Hello, everyone. Welcome to today's chemistry lesson. We're going to cover some really important topics: molecular formulas, empirical formulas, counting atoms using moles, identifying gases, balancing equations, and stoichiometry. Sounds like a lot, but don't worry, we'll take it step by step. Ready? Let's go. Right, let's start with naphthalene. Now, naphthalene is made of two benzene rings fused together. You know a single benzene ring has the molecular formula C6H6, right? But here's the clever bit. When two benzene rings are fused, they share two carbon atoms. So instead of adding up to C12H12, we subtract those shared carbons. That gives us C10H8. The key method here: always count atoms directly from the structure and subtract any shared atoms in fused rings.
Miss, why do we subtract the shared carbons? Aren't they still there?
Great question. Yes, the shared carbons are still there, but they belong to both rings. If we counted them twice, we'd be double counting. Think of it like two rooms sharing a wall. You don't count that wall twice when measuring the total, do you? Same idea with fused rings. Now let's talk about empirical formulas. Here's a good one: magnesium azide. Magnesium forms an ion with a 2+ charge, that's Mg2+, and azide, that's N3- with a 1- charge. To balance the charges, we need two azide ions for every magnesium ion. So the formula is Mg(N3), 2, which expands to MgN6. The method? Balance the ionic charges, then write the simplest whole number ratio.
Wait, so the empirical formula isn't always the same as the chemical formula?
Exactly right. The empirical formula is the simplest ratio. Sometimes it's the same as the molecular formula. Sometimes it isn't. In this case, MgN6 is the simplest ratio because magnesium azide is an ionic compound. Well spotted. Next up, how many oxygen atoms are in 0.0100 moles of sulfuric acid, H2SO4? First, look at the formula. Each molecule of H2SO4 contains 4 oxygen atoms. So, moles of oxygen atoms equals 4 times 0.0100, which gives us 0.0400 moles. Now multiply by Avogadro's constant, 6.020 times 10 to the power 23. That gives us 2.408 times 10 to the power 22 oxygen atoms. Remember the method: moles times atoms per molecule times Avogadro's constant.
Is Avogadro's constant always 6.02 times 10 to the 23?
Yes, it's a fixed number. 6.02 times 10 to the power 23. It tells you how many particles are in 1 mole of any substance. It's one of the most important numbers in chemistry. All right, here's a detective question. We have a gas in a flask. Same temperature and pressure, same volume, so the same number of moles, which is 4.0 times 10 to the minus 3 moles. The mass is 0.160 grams. To find the relative molecular mass, we divide mass by moles. 0.160 divided by 0.004 equals 40. Now, which gas has a relative molecular mass of 40? It's argon. Not helium at 4, not neon at 20, not carbon dioxide at 44. Argon at exactly 40.
How do we know it's not carbon dioxide? That's close to 40, isn't it?
Good thinking. But carbon dioxide has a relative molecular mass of 44, not 40. In chemistry, precision matters. 40 matches argon perfectly. Always compare your calculated value with known molar masses. Now, balancing equations. This one's about diphosphane. The trick is to balance the trickiest elements first. Start with phosphorus. We need 2 molecules of P2H4 to get our phosphorus atoms balanced. Then balance hydrogen. That gives us 4 H2O molecules. Finally, count up all the oxygen atoms. We need 14 total, so that's 7 O2 molecules. The answer: X equals 2, Y equals 7, Z equals 4. The method? Balance non-hydrogen, non-oxygen atoms first, then hydrogen, then oxygen last.
Why do we always save oxygen for last?
Because oxygen often appears in multiple places in an equation, in the reactants and products. If you try to balance it first, you'll keep having to change other numbers. Save it for last, and everything falls into place much more easily. Nearly there. Question 6. If we put 10 grams of copper into silver nitrate solution, how much silver do we collect? First, convert mass to moles. 10 divided by 63.5 gives about 0.158 moles of copper. The equation tells us 1 mole of copper gives 2 moles of silver, so we get 0.316 moles of silver. Multiply by silver's atomic mass, 108, and we get about 34 grams. That's between 20 and 40 grams. The method: mass to moles, use the mole ratio, then back to mass. Last one, when calcium nitrate decomposes, we need to find the total volume of gas produced. The equation shows 2 moles of calcium nitrate produce 5 moles of gas. So 1 mole gives 2.5 moles of gas. We have 0.050 moles, which gives us 0.125 moles of gas. At room temperature and pressure, 1 mole of gas occupies 24 d-meters cubed. So 0.125 times 24 equals 3.00 d-meters cubed. Remember, always use mole ratios, then multiply by the molar volume.
Miss, what if the question gives a different temperature? Do we still use 24?
Brilliant question. No, 24 d-meters cubed per mole is only valid at room temperature and pressure, which is 25 degrees Celsius and 1 atmosphere. If conditions change, you'd need to use the ideal gas equation instead. But for your EDEXCEL exam, they'll usually tell you which value to use. And that's it. Fantastic work today, everyone. Let's recap our key methods. Count atoms from structures. Balance ionic charges for empirical formulas. Use Avogadro's constant for counting particles. Calculate relative molecular mass to identify substances. Balance equations systematically. And always use the mass to moles to mass method for stoichiometry. Practice these, and you'll be ready for any question they throw at you. See you next time.